Okay, so now we're going to start talking about some classic parsing methods for natural language processing. Some of those techniques are also used for parsing non-human languages, for example, programming languages. That's why they have been developed many years ago. Some of them are in the 50s and 60s. I should say that even though those methods are pretty old, they're still being used with some modifications, as you can expect even these days. So it's important to understand how they work and where the people who came up with them were coming from. So again, let's look at the most typical example of parsing. We have on the left-hand side now a parse tree for the sentence, "The child ate the cake with a fork." On the right-hand side, we have a grammar. So the question is, how do we arrive at this parse tree given the grammar and given the original sentence as a string? So one of the approaches is to treat parsing as a search problem. And there are two types of constraints. Some of those constraints come from the input sentence, so we know that it has a certain number of words, that they come in a certain order, and that they have certain parts of speech. And there are other constraints that come from the grammar. So we know that what we're looking for is a sentence or a noun phrase, and that the sentence has a noun phrase and a verb phrase in that order, and that we expect to see an adjective before the noun. And so those types of constraints, both of them help constrain the parse process. So there are two general approaches to parsing as search. One is a top-down method, where you start from the sentence level and you try to expand until you reach a tree structure that matches the input string. Or you can also have the so-called bottom-up method, where you start from the sentence itself and you try to combine adjacent words into constituents and then combine those constituents together until you reach the S level at the top. So here's a very simple example of top-down parsing. On the right-hand side, we have the same grammar. Then we're starting from S, and we're trying to come up with a parse for the sentence. So the first thing we can try is S goes to NPVP. That's kind of unambiguous in this example. Then the noun phrase, the one thing that we can try, again, not necessarily by leftmost derivation, just for some reason we want to choose this particular expansion, NP goes to NPPP. And then it turns out that eventually this is going to conflict with the input sentence, which is that the first two words are "the child." So the prepositional phrase is nowhere to be found near the beginning of the sentence, and therefore we have to backtrack and consider a different interpretation for noun phrase, specifically determiner and noun. And later, if we expand this further down to the sentence, this particular derivation is going to match the input sentence, and we can proceed with the right-hand side of the grammar until we finish parsing the entire sentence. So this is an example of top-down parsing, and it was successful in this case with a little bit of backtracking. Now let's look at bottom-up parsing. In bottom-up parsing, we're going to start from the sentence, "The child ate the cake with the fork." And we're going to try to combine symbols starting from the left-hand side. So "the" is the only thing that it can be is a determiner, "child" is a noun, and so on. We get all the parts of speech, and we move on. We try now to combine left to right the determiner with something else to build a new non-terminal from the grammar. So determiner noun combined very nicely into a noun phrase. Then we have now a noun phrase and a verb phrase. We could combine those two together, or we can combine another determiner and a noun into a noun phrase, and possibly a third one. Then we can combine the prepositional phrase with the noun phrase, the preposition with the noun phrase to form a prepositional phrase. And now we can combine a noun phrase with the prepositional phrase to form a new noun phrase, and so on. As you can see, at every iteration, we are picking two symbols that have not been combined yet, and we combine them together until we reach the top level of the sentence, S. And now, when I say two, this is just because this grammar is of the so-called binarized form, in which case the right-hand side of a non-terminal is always consists of two new non-terminals. This is not necessarily the case in general, as if you remember, the grammar with auxiliaries had rules of the kind S goes to auxiliary, noun phrase, verb phrase, in which case you have three things on the right-hand side. It turns out that for parsing, it's very important whether grammar is binarized or not. We will revisit this in the next few slides. So there are some advantages in both the bottom-up and the top-down methods, and there are just as many disadvantages for each of them. So for example, the bottom-up parser has a significant problem, is that it explores options that are not going to lead to a full parse. And this is pretty obvious since we're starting from the sentences. And the top-down method has a different problem. It explores options that don't match the full sentence. So you may have a dead end starting from the top, and then you have to do a lot of backtracking until you find the correct expansion. So one technique that solves some of those problems is based on dynamic programming. So just to remind you, dynamic programming is a method where you have a number of iterations. At each iteration, you combine some solutions, some partial solutions that you have computed in the previous iterations to form a solution to a larger problem. So you essentially cache a lot of intermediate results, for example, the particular parse of a noun phrase, so that you don't have to reparse it later on. So the technical term for this caching is memoization, not to be confused with memorization. Memoization just means that once you have a non-terminal that has already been parsed, you can just store all the information that was needed to parse it, and you can just restore it from memory instead of recomputing it every time you need it. So the method that has been used the longest, that uses dynamic programming for parsing, is the so-called Koki-Kasami-Younger parser, or CKY. As I mentioned before, it's based on dynamic programming, and it's actually very powerful as long as the grammar is in a binarized form. So now we're going to look at some specific techniques for parsing. We're going to start with shift-reduce parsing. So shift-reduce parsing is a bottom-up parser. It goes left to right in the sentence, and it tries to match the right-hand side of a production until it can build a sentence. It includes two operations. As the name indicates, those are the shift operation and the reduce operation. The shift operation takes a word from the input sentence and pushes it onto a stack. So for example, if the sentence is, "The child ate the cake with a fork," the first thing that we'll see is that the word "the" is going to be pushed onto the stack. And then it will wait until it can be combined with some other word. And then if that happens, it will perform the so-called reduce operation, which checks if the top n words on the top of the stack match the right-hand side of a production. If they do, then all of them are popped from the stack, and they're replaced by the left-hand side of the production. For example, if we had the word "the" already on the stack, and the next word is child, the word "the" is a determiner, the word child is a noun, and we have a rule that says that a determiner and a noun can be combined to form a noun phrase. So once we have pushed "the" and child to the top of the stack and we pop them back, we're going to replace them with the symbol for noun phrase. And there's a stopping condition. This one should be pretty obvious. This method is going to stop if both of those things are true, namely that the input sentence has been processed all the way to the end, and that an S has been popped from the stack and there's nothing left in the stack. So let me now walk you through an example of a shift-reduce parsing process. What you see on the screen is the sentence that we want to parse. The child ate the cake. There is a star that tells us how far in the string we have gone. At the beginning, obviously, we are at the beginning of the string. So the only thing that we can do at this point is to recognize that the word "the" is a word and that it has to be pushed into the stack using a shift operation. So we're moving the cursor forward, and we now have the word "the" on top of the stack, and we replace it there with a determiner. So determiner is its part of speech. So this is done using a reduce operation. So now at this point, the stack has determiner on top, and child ate the cake remains in the string. So the next thing that we want to do here is to process the word child. So the word child gets pushed onto the stack and then replaced with a noun. So with a shift and a reduce operation, we have determiner noun on top of the stack and ate the cake as the remainder of the string. So at this point, we can perform a second reduce operation to merge the determiner and the noun and replace them with a noun phrase. The next thing we do is look at the word ate. The word ate goes to the stack. Then it gets replaced with its part of speech, which is verb. And then the noun phrase and the verb are going to be combined together, and so on. So we have a sequence of shifts and reduce operations until we get to this point where we have on the stack three categories: noun, phrase, verb, and determiner, and the word cake. So the word cake gets replaced by a noun. And then at this point, we can combine things on the top of the stack, determiner, noun into noun phrase, verb noun phrase into a verb phrase, and finally noun phrase verb phrase into an S. So at this point we have satisfied all the stopping conditions when we can declare that the parsing was successful. So just to remind you, the stopping conditions were that the stack is empty, the input string is empty, and that we have been able to get S as part of the process. And the corresponding parse tree here is S goes to noun phrase, verb phrase, and so on. So the next thing that we're going to talk about is the Koki-Kasami-Younger parsing method, or CKY. It's based on dynamic programming. And the reason why we're using dynamic programming is so that a lot of the work that is normally repeated in parsing, bottom-up or top-down parsing, doesn't have to be repeated. So we're going to cache some of the intermediate results in order to improve the complexity of the parsing algorithm. So the dynamic programming method works the following way. You're going to build a parse for a substring from word I to word J based on all the current parsers I to K and K to J, where K is somewhere between I and J. So for example, if we have something like the child ate the cake, we're going to parse that phrase, the child ate the cake, based on the parses for the child and the parse for ate the cake, or any other combination of substrings for this 5-word sequence. So the complexity of dynamic programming is cubic, and this is for recognizing or finding a single parse for any input string of length n. We're going to look at more detail at the complexity of CKY in a few slides. So the CKY method is a bottom-up method, and it requires that the grammar is normalized. More specifically, it has to be converted to a binary form. So in a binary grammar, the only things that you're allowed to have is a non-terminal going to 2 non-terminals, or a non-terminal going to a terminal. Later, we're also going to look at the early parser, which is also based on dynamic programming, which is a top-down parser, and a little bit more complicated than CKY, but more importantly, doesn't have this binarization requirement. So going back to CKY, the sentence that we want to parse is the same. The child ate the cake with a fork. The grammar is the same, and as you can see, it is in binary form. Let's confirm this. S goes to NPVP. There are 2 non-terminals. This is fine. Both rules for noun phrases include 2 non-terminals on the right-hand side, so this is fine. The same thing applies for prepositional phrases and verb phrases. And then finally, we have the lexicon. All of the non-terminals here, determinant, noun, preposition, and verb, turn into single terminals. And again, this is completely consistent with the definition of a binary grammar. So the CKY method works by building a dynamic table. Each of those cells here tells you how to parse a substring of the original sentence from a given word to another given word. So for example, at the very beginning, we want to build a parse for the word the. So the word the, looking at the lexicon, is a determiner. So this cell here includes the information that the word the is a determiner. Then we're going to start filling this table until we get all of the boxes full. And the order in which this is done is by columns going bottom up. So the next thing that we're going to produce after this determiner is the box just between child and ate. So the word child is a noun, according to the lexicon. The next box is the one above. So is there any way to combine a determiner and a noun? Yes, there is such a way, and that is by creating a role for noun phrases. And we can also keep some back pointers that tell us that this noun phrase was created from the determiner and the noun. So the next box that needs to be expanded is the one to the right of the word ate. Well, that's a verb. There's only one possible way to interpret this word in the grammar. Then there's nothing else that we can do in that column. We move on to the next column. The word the is a determiner. And again, the boxes above cannot be filled at this point because there's no rule that has a determiner as the right-hand side. The word cake now is a noun. At this point, we can combine the determiner for the with the noun for cake. That gives us a noun phrase in this particular cell here, which with back pointers takes us to the parses of the individual constituents, determiner and noun. Then we continue filling the rest of this column going up. So there is a verb phrase that can be produced by combining the verb 8 with the noun phrase the cake. So this is what you see on the screen now. And we can also go all the way up to the cell that goes from the to cake. In this case, we can build a sentence right there. And this sentence consists of the noun phrase the child and the verb phrase ate the cake. Now, one thing that you can say at this point is, okay, aren't we done? Can we just parse the input sentence? Now, obviously, we're not done because we still have the words with the fork that have to be processed. We have been able to identify a sentence up to this point, the child ate the cake, but we're not done. We have to continue until we can find an S in the top right-hand box of the chart. Okay, so what do we need to do next? We need to expand the word with. That's a preposition. There's nothing we can do with this preposition on the right-hand side, so the rest of the boxes in this column are going to remain blank. The next word then is the word the, then fork. Then we can combine the determiner for the with the noun for fork to get a noun phrase. We can combine that noun phrase with the prepositional phrase with the preposition with to form a prepositional phrase. And finally, we can combine the noun phrase the cake with the prepositional phrase with the fork to form a noun phrase that corresponds to the substring the cake with the fork. So this is where we are now. We can continue going up. We now have an entire verb phrase that we obtained by combining the verb phrase ate the cake with the prepositional phrase with the fork, and that gives us a new verb phrase ate the cake with the fork. But we can also combine a verb phrase at this point by merging ate, which is a verb, with the noun phrase the cake with the fork. So you can see that we have a verb phrase in this cell, but it can be obtained in two different ways, and this obviously will lead us to having two alternative parsers for this sentence. And eventually, we have this verb phrase can be combined with the noun phrase, the child, to form the sentence, the child ate the cake with a fork. But as we noticed before, there are two different parsers that have to do with the verb phrase ate the cake with a fork. So if you look at the CKY data structure, you will see that the both lines tell you that the verb phrase in position 8 can be obtained by either combining of the verb and a noun phrase or by combining a verb phrase and a prepositional phrase. So this gives us two different parsers, and we want to figure out what is the meaning of each of those two sentences, the one on the left and the one on the right. So what's the difference between the two? Let's look at the syntactic tree. The one on the left-hand side has the prepositional phrase with the fork as part of the cake with the fork. So it's part of the noun phrase, whereas the one on the right-hand side has with the fork at the same level as ate. So to remind you, we have looked at examples like this before. The one on the left-hand side is an example of noun attachment or low attachment, and the one on the right-hand side is an example of a high attachment, also known as verb attachment. And the semantics of the sentence on the left is that the cake includes a fork, whereas the one on the right-hand side says that the fork was used to eat the cake. And this is the Penn-tree bank representation of those sentences. As you can see, the first one has S goes to NPVP and the VP goes to VPPP, whereas the second one, the S goes to NPVP just as before, but the verb phrase goes to VNP, and then the PP is generated as part of the noun phrase instead of directly as part of the verb phrase. If you're interested, there's a nice online demo of CKY parser, which actually uses a very similar example to the one that we looked at so far. Feel free to take a look at the site and return here. So one thing that we want to say about the complexity of CKY is that there are O of n squared cells in the table. Specifically, there are n times n plus 1 divided by 2 cells, but it is still order of n squared. For finding a single parse, you have to do a linear lookup through each cell, so that's a square algorithm. And then you have to do this n times, so the total time complexity is O of n cubed. However, if you want to find all the parses, the total time complexity is going to be exponential, not cubic. And there is a reason for that, and we'll get to that in a second. Now let's look at a longer example. So this grammar here, which we've seen before, has non-binarized rules. For example, it has the possibility of creating imperative sentences, VP going directly to a V, auxiliaries now before the noun phrases, and so on. So if you want to parse the sentence, take this book, which is an imperative sentence, we have to use the grammar that we have on the slide. And because it's not binarized, we cannot use CKY as it is. We have to first convert the grammar to a binarized format. So here are some of the non-binary productions. S goes to auxiliary noun phrase, verb phrase. This is non-binarized because it has 3 non-terminals on the right-hand side. S goes to VP, NP goes to pronoun, and so on are all unary rules which have to be converted to binary as well. So this leads us to the binarized form of this grammar. The technical term for it is a Chomsky normal form, or CNF. It tells us that the grammar has to be in the following form: either a non-terminal going to 2 non-terminals or a non-terminal going to a terminal. So to convert the grammar from the previous slide, we have to create new non-terminals for hybrid rules. So a hybrid rule is one that has a mixture of terminals and non-terminals on the right-hand side. For n-ary rules where n is other than 2. And for unary rules where n is equal to 1. So here's an example from the 80s grammar described in Jurafsky and Martin. The original grammar is shown on the left. We have 2 examples of non-binary productions. S goes to auxiliary noun phrase, verb phrase, and S goes to verb phrase. So how do we convert those to binary form? Well, one possibility is to split the 3-way right-hand side of auxiliary noun phrase, verb phrase into 2 binary rules by introducing a new non-terminal called x1. So we have S goes to x1 VP and x1 goes to auxiliary NP. So this way, the new grammar is in CNF. Now, the unary cases are more complicated, and they involve a specific procedure, which is going to take possibly some of the terminal symbols so that the grammar can be turned into Chomsky normal form. So in this case, S goes to VP in the original grammar is going to be replaced by several new rules, some of which directly take you to the terminals such as S goes to book, include, and prefer, and others that expand the sentence S into 2 non-terminals, each of which having exactly 2 non-terminals. So S goes to verb and noun phrase, and S goes to VP, PP. And you can do the same thing for all of the other productions. So for example, NP goes to pronoun is going to be replaced directly with NP goes to I, or he, or she, or me. NP goes to proper noun is going to be replaced directly with the terminals NP goes to either Houston or Northwest Airlines, and so on. So there is an automated procedure that takes the original grammar and binarizes it and turns it into Chomsky normal form. So here's some specific examples. An infinitival verb phrase that is 2 verb phrase would become something like infinitival verb phrase followed by 2 as the preposition's non-terminal symbol. And then that new non-terminal symbol is going to be converted into the terminal symbol 2. S goes to auxiliary noun phrase, verb phrase is going to be replaced with S goes to R1 or X1 VP, R1 goes to auxiliary noun phrase. And finally, all the unary rules will be converted into rules where the left-hand side is a non-terminal and the right-hand side is a terminal. So there are some issues with CKY when we start from a non-binary grammar. It turns out that the language generated by that new grammar is only weakly equivalent to the original language. It generates the same strings using the different derivations. So if we have to convert the original grammar to Chomsky normal form, then the final parse tree is not going to match the original grammar. So some additional processing will need to be done to convert it. And this is something relatively straightforward to do, but it needs to be done. One other issue with CKY parsing is that you can have syntactic ambiguities. So the deterministic CKY method has no way to perform syntactic disambiguation. So in the sentence, the child ate the cake with a fork, we saw that the chart includes 2 possible parsers, but the parser has no way to tell which one is the best one. It would need to use either probabilities or some additional external information to choose one over the other. And we'll see how this can be done later on. Okay, so as we can see, CKY is a very reasonable parser. However, it has some issues that can be addressed using some other techniques. We're going to look at some of those other techniques in the next segment.